Okay. So as I said, today we are looking into dynamics. So dynamics in computational context means we are having, or we are assuming that we have any transient solution that we want to obtain, and that involves time-dependent variables. Time-dependent variables are, of course, with respect to displacements, it's time differentiation, that means velocities. And further differentiation, we end up with accelerations. Okay, let's assume we have any physical thing happening that we want to numerically describe as in a model such that we can also build up simulations out of this. We have a function of acceleration here in a graph over the time. And just as in displacement theory, we have to discretize this somehow, because as this is a continuous function in time, it's really hard to have this in a discretized in a numerical sense, so that a computer can actually actually deal with it. Our temporal discretization means that we used to discretize this function at discrete time steps. So here we assume we have a time step or a certain position in time that I call Tn here. That's just one point in time, and another time step Tn plus 1. That's another discrete point in time. And just as in displacements, so in displacements you have a body which is displaced somehow, and you can see that in finite elements, for example, where we have discretized this body with a mesh, each element in this mesh has a node, at least one, and at this node we discretize this displacement. In between the nodes we have any sort of interpolation, but the actual discrete displacement is only known at the nodes. So here we are using the equivalent in temporal discretization, where we have at these time steps a certain discrete point of the acceleration function here in time. In between these time steps, we define the time step size, which is delta t. Delta t means this is the time difference from one specific point in time to the other. Also, we have the concerning values of that function that we can mark here on the y-axis. So that means here we have the acceleration n plus 1 and the acceleration n, where an would be the acceleration function evaluated at time Tn. Okay, so from this drawing we say, suppose any quantity at time step n to be known. And now the acceleration is not specifically what we are aiming to have in the end. As I said, we will use the displacements on the mechanical field in this course that we want to compute. And if any acceleration occurs in our dynamic analysis, which usually does, then we have to somehow relate it to the displacements. And for this relation, we need any sort of time integration methods. So there's several examples for such integration methods. Most famous one is an Euler explicit scheme. Which is also existing in an implicit version, and the famous Newmax scheme. Okay, in this course we will use the Newmax scheme. The Newmax scheme was also part of FEM2, and we will just give a little recap here. So once more, the target is to relate the displacements to the velocities and to the accelerations. And we will start with the derivation, or with giving the idea of Newmax method here, starting with the acceleration. So the main assumption of the Newmax scheme is that within such a time step, the acceleration is constant. So we are approximating this continuous function, which we don't know about, with a constant value. Yeah, that's basically it. From this constant value, we can apply time integration following the very simple formulas. So, and with this, we obtain our new velocity, the velocity at time step Tn plus 1, which we don't know yet about, to be the velocity at time step n plus the increment. And the increment is nothing more than the time integration of the acceleration, with the assumption that the acceleration is a constant. We can write like so. So the constant times the time step size would be the integration here. And as you can notice, the constant that we've chosen is indeed the mean value between the known acceleration an and the yet unknown acceleration an plus 1. Further, we use the same strategy to get an expression for the displacements here. So basically we're saying the new displacement is the old displacement plus an increment from the old velocity integrated in time, plus the increment from the twice integrated acceleration here, and down the line inserting everything that leads to un plus vn delta t. Okay, and as a result here, we get an expression for the new displacement in terms of the old displacement, which is known. Remember, we suppose that all values with subscript n here at time Tn are known. So the expression for the new displacement is based on the old displacement, the old velocity times the known time step size, the new acceleration and the old acceleration value. So basically, if you look at these two formulas here, the only unknown is an plus 1. So In other words, if somehow you can calculate the new the acceleration at the new time step Tn, then you are also able with these formulas to tell the velocity and the displacements for the new time step. If you ask me like, okay, I have nothing won by this because I don't know about the new acceleration, think about a formula like this, where you say A is equal to F divided by M, which is Newton's law. So once you have forces and masses known, you can compute an acceleration. However, in this case, you will compute the acceleration first, and then from the acceleration, compute velocities and displacements. However, we have another strategy here in place because we agreed that the displacements is our main field. So with a little math, you can invert these formulas. By this, you will have formulas for the velocities and the acceleration at the new time step in terms of the displacements at the new time step. This is just applying some math, which I will definitely upload the derivations, but I'll skip it here because it's not black magic, it's simple math. You can invert these coupled formulas here to achieve the following. Oh, sorry. So as I said, a formula for the acceleration with the only unknown here is the new displacement, and the formula for the velocity with the only unknown also being the displacement. Again, following the assumption that all values with subscript n are known. That's the displacement, the velocity, the acceleration, all at time step n, and here again the displacement and the velocity. Okay, you don't need to know for this course, or you don't need to know by heart how to derive these formulas from the assumptions that we just started with. However, we will use these formulas for the numerical implementation, not only today, but also for the finite elements in the future. So you should, from all of this, have an understanding that in the numerical sense, we divide the time, the continuous time, into time steps, and the beginning and end of each time step is supposed to be a discrete point in time where we discretize all fields. So at this point, we have a discrete displacement, and with these very formulas, we can, from this discrete displacement, compute a discrete acceleration and a discrete velocity. Also, you can already get the concept that if you are relying on these formulas, as I so often repeated already, you need to know certain things. You need to know the current displacement, the previous displacement. By previous, I mean at time step n. You need the displacement, the velocity, and the acceleration. or you can easily imagine, starting values for these are easy to find. You can start, for example, with 0. If you have a system at rest, every velocity, every acceleration, and any displacement is 0. And let's say you load it. From this loading condition, you will see any deformation. Computing deformation, all of you have done this before, so all of a sudden you have a certain displacement. And now I ask you for the acceleration and velocity at this result, at this time step, and you can just insert all the known quantities, which were 0 before, into these formulas. That's basically it. So because we will need this further down the line, we are already thinking about derivatives here, and we will need the derivatives of the acceleration with respect to un plus 1, so with respect to the new displacement. And that would be simply the factor 4 by delta t squared. I'm also introducing dv here. Which is the factor 2 by delta t. And for those who really remember what I'm talking about, the Newmark formulas do include in their full form some gamma and beta parameters. Here we have the specific values, gamma equal to, let me check, gamma equal to 1/2 and beta equal to 1/4, which results exactly in these formulas. But if you're interested, as I said, I will upload the sheet with all the derivations about this, so you are able to follow this in detail if you're interested. And there, at a certain point, these parameters are introduced. Okay, so suppose everyone's on board with me at this point. We can think about how to apply this time integration. And you can also see this as kind of a recap on how to solve numerical problems. So we will talk about a single mass oscillator, which is a nice little problem. Of course, a model problem. So it's really hard to find a physical equivalent for that, where we have, but the idea is, or the model is that we have a mass. The mass is attached, or is of course, has a certain mass, m. It is attached on the one side with a spring to a rigid surface. The spring has a certain stiffness k. And on its right-hand side here, we apply a damper, and the damper has a certain damping coefficient d. There is a differential equation to describe this problem, which is this little guy here. Also quite popular, you might recognize. The dot over a quantity here in this sense is means a differentiation with respect to time. So x dot would be the velocity, the first differentiation of the position with respect to time, and x dot dot the acceleration. Further, I've introduced here an external force. So that's what I'm missing here. So the mass is or might be loaded with such an external force here. And we introduce a coordinate system here as well. We start with this at the center of mass. At the initial position here, we place our coordinate system x. That means x and u. So x in the initial case would be 0. And if we say that xn plus 1, so the new x would be the initial x plus a certain displacement. With this in mind, we can say for this specific problem, we have an equivalence of u and x. And so let me write this system as such, and all of a sudden we have the accelerations with an a, the velocities with a v, and our displacements here in the game. And if you think about this bare function as it is here, let's say f external is known, then you can say with what I know before, I can transfer this system of equations. It's not a system of equations. This differential equation, I can transform that to a form such that the only independent variable here is the displacement. So we might say m times a, and a can be a function of the displacement, plus d times v as a function of the displacement, plus k times u minus f external is equal to 0. And let me call this guy g a function of u. So in this case, we have a differential equation which we will not transfer into weak form first, but because it's not necessary here. In finite elements, we would do this usually, and this is what we will take recap also in the next session. However, bear with me here that we have the similarity to the finite element method, where we have a function of a certain unknown or a certain field of unknown, which we would like to solve. Great. Okay, further, we are introducing our time discretization here, because if you think about the formulas, which we will also use in a second of the Newmark scheme, they involve this delta t here. So delta t must be known. And you can imagine, if you just think about it, that this must have an effect on the acceleration and velocity. So from my little example, where for the sake of simplicity, I said you have a body at rest, and with a certain force, you can compute a deformation. And now I'm asking about acceleration and velocity. Of course, the time that it took to get from here to there has an impact on the acceleration and velocity. Also, on a very simple example, if you have a certain displacement here computed and I ask for the velocity, if you think about the displacement being, the velocity being constant, just as an assumption, you would simply divide the displacement you computed by the time that it has taken to be there. And that will be the division by delta t here. So delta t has an impact, and therefore we discretize in time. So Tn plus 1 is equal to Tn plus delta t. Further, we say that our Un plus 1 is equal to un plus delta u. So we know un at the beginning or at the previous time step. We compute any sort of increment to that, and this increment together with the previously known displacement is our new displacement. You might recognize this is exactly what we use in a Newmark scheme, even without dynamics. Sorry, in a Newton scheme. Then once more, our accelerations would be, in this case, a function of un plus 1. So here I'm just repeating the formulas of Newmark that we have written above. Okay, so with all of this, we aim to solve the equation g of u is equal to 0. And because we assume generally that we could face a nonlinearity here, by the way, we will have at the end of this course a nonlinearity due to coupling, even with linear theory to both the temperature field and the displacement field. And therefore, we intend to use the Newmark scheme here as well. Sorry, Newton scheme, Newton. That means we use the Taylor expansion, g of u plus g with respect to u times delta u equal to 0 at the equilibrium that we are looking for. And that leads to the algorithm where we initialize a delta u with respect to, not with respect, but with 0. And then we say while g of u, while we use the norm here, is not equal to 0. We say delta u is equal to delta u minus g by u inverse g of u. And here we use, of course, un plus delta u. Okay, so once more, this is the same Newton scheme that we use in the finite element method and which we will use in this course as well. Here, this formula g of u, this function is scalar. So this inverse here technically means 1 over the number. However, in finite element, we are dealing with this in a vectorial sense. So this will become a matrix, the so-called stiffness matrix of the system, which will be inverted. This will be the right-hand side vector of the system, and this will be the increment vector. Still, here this is 1D, so it's a little more simple. Un is left unchanged for the whole Newton scheme. So we have a certain point in time that we know everything about. We know also the displacement at this point. And then we have any sort of loading situation, which leads to G of U being unequal to 0, so no equilibrium. And we are searching for the displacement increment, delta U, that is necessary so that G of U is 0 again. For that, we initialize a delta U, a potential delta U to 0. And then in this loop here, we increment delta U by this term here. And to evaluate this term, we use UN, which is completely the same for all evaluation of this Newton loop. And just delta U changes. It's 0 in the first place, and in the second place, 0 minus whatever results this term in the first iteration of this loop. Okay. Okay, so now the time stepping thing comes into play. From our my simple example, so the body is elongated now, we have a certain displacement. The displacement is computed in terms of a increment, delta U. We were starting with 0 in the beginning everywhere, 0 velocity, displacement, and acceleration. Now we have a displacement. So we just said we can compute for this displacement also the acceleration and velocity based on the formulas we had. And we need to save these variables in view of the next time step. So if you think about an actual dynamic analysis, there is not one final result for the next time step that we are looking for, but maybe we are looking for the next 100 results for the next 100 time steps. And as we proceed, repeat the procedure over and over again, we need to make sure that we have all the information in the next time step that we need. And what we need is, at the beginning of a time step, we need to know acceleration, velocity, and displacements. And this is what we will now prepare in view of this next time step. So we will have A, or we will start with the displacement, U, n plus 1 is equal to UN plus delta U, obvious. Then we can compute Vn plus 1, which is V evaluated at UN plus 1 with the very formula that we have written down twice, and An plus 1 in the same fashion. And in view of the next step, where we need UN, An, and Vn again, we shift them in time. And that, guys, is the typical history variable scheme. So this happens a lot in finite elements and other numerical codes. you have a certain set of variables that need this kind of update scheme so that they are available at the next time step. And there's usually a certain procedure to follow, depending on the software, to make the code handle these variables just so. Whether the shift, so UN becomes UN plus 1, happens at the end of a time step or at the beginning of a time step, depends on the software. So that might be a little different. And of course, we will not only use this behavior or mimic this behavior in our code in a second, but I will explain to you how this happens in the finite element code that we will use actually in the same way. All right, so what do we need to prepare for this code? We do it very similar to the finite element method. In the finite element method or an algorithm, I'm talking about the code, so to speak, you have a finite element subroutine. A finite element subroutine is nothing more than a function which has input parameters. Usually the input are material parameters, the input are displacements and nodal positions, and in time of temporal analysis, also history fields. We will write an oscillator function here. Oh, sorry, I missed. The important part is that these finite element subroutine should return the element vector and element matrix, which are the right-hand side of the governing equation and the left-hand side, or the tangent of the governing equation. And we will do the same here with a little oscillator function, where we return G. Or let me put this another way. So we will prepare a function which takes as arguments material parameter. Mat would be a vector of material parameters. And if you face or remember our differential equation, what we would need is a mass, the stiffness of the spring, the damping parameter of the damper, and also the time step size. U is simply the current displacement of the system. Which is UN plus delta U, whatever delta U is, so that we can call this function within the Newton scheme, where delta U is modified outside this function. And at last we have here HN. So HN will be a vector of our history parameters. Because we said for all of these equations to work, we need to know the current or the previous displacement, velocity, and acceleration. What we return is G. G is a scalar in the scalar equation, and that's simply the evaluation of m times a plus d times v plus k times u. And we need to return dg, which is the tangent of g with respect to the degrees of freedom, which are the displacements here in this case. So we concluded before, a and v are functions of that displacement here in this scheme. So we would say m dA du plus d dv du plus k du, which is 1. And also the other derivatives we have formed before, which were the factors 4 over delta t squared. And here we had 2 by delta t. And this is k, obviously. So an interesting point here at this to recognize here is that dg is constant. It does not depend on the current degree of freedom, which means that we have a linear equation here. If the tangent is constant, the equation above the tangent, or where the tangent was derived, is linear in the degree of freedom. There is a question in the chat about the external force here. And very important, I'm not a professor. Thank you for the promotion, but my salary is way below that. If you missed that, my name is Sasha, and you can just call me Sasha, not Professor or Professor Sasha. The external force, no worries. The external force must be included at a certain point in our solution scheme, of course. But the external force is not part of our oscillator function here, because we try to mimic the finite element as algorithm as best as possible. And the equivalent of an external force in the finite element scheme would be the force vector, or there are many names for this, but if you, like in Pheeb or other finite element programs, define a Neumann boundary condition or a nodal force as a boundary condition, this is called external. And that, if you remember, is not included in the finite element subroutine. But when the algorithm forms within the Newmark scheme, this guy over here, then it adds the external forces automatically on top of it. And this is, we will just do it in the same fashion. So if you have never spent a thought on it, it's fine, but this is what happens in the background. If you define a boundary condition force in the input, this is not computed from the finite elements, but just from the finite element program, and it is included at this very step in the algorithm. So it's not part of the finite element function. There are few exceptions for non-conservative forces or for boundary elements that serve a specific case. But so you can do this, but as I said, this is not the common case. Okay. So we have G, we have dg, and see here, we return an H. This H is a history field. And this H will be the history field updated so that if it turns out that the current delta U, which was used for the current input of this function, leads to this guy here to be actually 0, that would mean we have reached an equilibrium and we are satisfied with our solution. And then we need to provide these 3 guys so that the algorithm can provide them for the next time step. Remember the input of the function hn, this is all the n values, and we export the h values for usage in the next time step. There is one point here why we have a difference between the input here and the output, which is this update here. This is only performed if we have reached an equilibrium state. Otherwise, we would have spoiled all the n values before this right-hand side of this part here would be valid. Because if we compute un plus 1 from a non-equilibrium delta u, the un is also false that we get from this. Also, these guys here are computed from the chosen time integration scheme. We use the Newmark scheme here, but this is part of the finite element. Remember when you, or imagine if you program a finite element and you use a time integration scheme of choice, this is what is your job to implement. The finite element program as a whole doesn't know about the specific scheme you're using, and this is why you need to provide these values to the finite element program. Okay, so that would be the last job of this function here. To compute h, and h would be a n plus 1 v, sorry, n plus 1 and u n plus 1. How to compute these, we've written down several times before, and also recognize that these values must be computed before we compute g, because they are included here. And maybe I make that clear by calling these n plus 1, and un plus 1 would be also the input as described before. Okay, we will code this, or we will code a little algorithm to solve all of this from scratch. And for that, let me outline what we are planning to do. The program flow is, we have an initialization. For the material parameters, placement, and so on. And then we need to define an external force, because without any external force, nothing happens. Let's look at the differential equation here, ma plus dv etc. We just said we will start with all our variables initialized to 0. So our initial displacement is 0, our initial velocity and acceleration is 0. So whatever the material parameters, this becomes 0, 0, 0. So left-hand side of that equation is 0. And if f external is also 0, then we have equilibrium right from the beginning and nothing will happen. So we need to provide any sort of external loading. And I say here external loading function. Why? Because with a transient analysis like we are about to do, we need to take into account that also the external force might be a function of time. So we have function f of t, which will be our load, and t is the time here. Let me give you two examples. This is f, this is t. And we have just straight from the beginning, or I can put it in the same graph. F of t is equal to 1. So that would be a constant function, even though we technically use the argument of the function t. And we will investigate later why this can be problematic. And another function that we will use is a step function like this. Yeah, step function. It's a piecewise function. So we have, let me put that below here. So f of t is equal to like so, is equal to t if t is smaller than t0. T0 is just one parameter that we could choose. After we are t0, we jump accidentally to 0. So the idea is we have a function which is actually dependent on time and which scales linearly until a certain point in time is reached, and then we just make it go away. What effect that will have to the response of the system, we will see later. Then we have this, we have that, and then we can go into finding the solution for the time steps. Solution phase that will include a loop over time steps. So it's a loop, and within this loop we will call the Newton scheme to find delta U. So of course, as we increase time, maybe that's important, tn plus 1 is equal to tn plus delta t. Now let me maybe write this down here in a little more detail just once. Then in the Newton, we say our residual is equal to G, dg, and h is equal to oscillator. So U n plus 1 is equal to un plus delta U. N plus 1 is equal. That happens in the Newton scheme. Sorry. Let me put it this way. Times G. Okay, yeah. So now I got it. Sorry. So this is also precisely what we will actually program. Yeah. So we make a loop over all time steps. First thing happening in a time step is that we are increasing the time. Next step would be, because we assume with an assumption is not wrong, right? We assume that with an increased time step, we have to look for an equilibrium again. For that, we will apply the Newton scheme. First, before we get into the Newton scheme, we need to initialize the increment of the displacement to 0. In the Newton scheme, first thing we are doing is we are calling our oscillator function to get current G, dG, and the supposed to be correct history variables. The argument that we use for that is the displacement, which is known, plus the increment. And as discussed before, this will be 0 in the first iteration, but will change later on. Then, coming back to the good question we have discussed before, at this point, we need to include the external force here to get the actual right-hand side for the equation system. Because as seen here, we have not included the external force into this equation already. This is done by the program here in an external manner. And also see that we are using Tn plus 1 as the argument of the function here. So we are accounting for a change in the external force based on the new time step we just need to solve for. If this happens to be 0, then nothing happens at all. And we are just continuing in our algorithm. So the assumption that we have to solve for something is not a problem, because if equilibrium is there, we'll just continue. If this is not the case, if we have not reached an equilibrium here, we update our delta U, and with the updated delta U, we continue. So very important, a finite element program and the very finite element program that we will use works the same way. We have a Newton scheme. Inside this Newton scheme, we will call all the finite elements. Of course, the program then with more than one finite element has to assemble the right-hand side and stiffness matrix. Then the program takes care that on this right-hand side, the external forces are added on top. And then if the resulting right-hand side vector is in a certain criterion not satisfying equilibrium, then the linear system of equation is solved. Here, this is just a scalar expression, but it becomes a system in finite elements with more than 1 degree of freedom. Procedure is identical. So suppose that we have found an equilibrium and have exited this Newton loop. We update. We say that our UN plus 1, our UN becomes UN plus delta U, so that in the next time step, this will be used here. We use BN and AN. And that's actually an interesting point. Where do we get these from? These are gotten from the return of the oscillator subroutine. So it's computed within the subroutine. V will be the first and A the second entry. This indexing here to this parameter is already in view of Python, because one rather odd thing of Python with what you might have been used to is that in Python indexing starts with 0. So if we look at our H field here, this is the 0 entry, this is the 1 entry, and that's the 2 entry. And then I still have to correct myself. So A will be entry 0 and V will be entry 1. Okay, so far what we are planning to do. Anyone having questions to that? Okay, there is a question. Why this is not H2? Yes, you're right. That's identical. So we could also say that that we use the return of the oscillator function for that. The number should be the same, of course. Yeah. What will happen? So there's another question. What will happen if we have equilibrium condition at initial stage itself in our program? And the answer is nothing. We can just play it through, but also we can play with it in the code later. However, in this case, say we have wisely chosen a f of t function here equal to 0. So as I said, the general equation here, g, will be 0, right? We started with all 0 variables for displacement, velocity, and acceleration. Then the finite element program evaluates our external function at the new time step, which will be 0. So g is equal to g minus equal to 0 minus 0. And then at this point, we would check if g is smaller than a certain tolerance or the norm of g. The norm of 0 will be 0. Our tolerance will not be smaller than 0. And hence, we will just exit here and directly switch to update. What will we update? We will update everything in the history field. And as the history field will be computed from 0 initial variables, there will be zeros in it still. So nothing will happen. We will just repeat until these loops here, or this time loop here is finished with the very same result, that nothing happens. I'm a little confused with someone's mentioning that the if loop won't run. How so? Okay. So, okay. Yeah, I guess it's a good idea to jump into some programming. And for these curiosity questions, we can all answer them by trying. We are engineers, so this might be the best way of approaching it. For this case, where's my code? There we go. Okay, for bravery, I'm just sharing my whole desktop with you. And so this is Visual Studio Code. For those of you who prefer to work with anything other, this is just a text editor. So you can, I will just write down a Python script here, and you can do it in the same way on any other environment. what's the function of history variable is another question here. Let me answer this while we program it. So I hope then it gets clear. So what I'm starting with is I'm opening a new file. I will save it with, I don't know, x1.py. And by putting the ending .py and with the Python extension installed to Visual Studio Code, I get syntax highlighting for Python language and also the ability to run this script directly from Visual Studio Code by the run button over here. I think this was explained in the video that I shared in Moodle. For those who have not watched this, extension to this editor can be installed here via this extension tab. And if you put Python in the search field over here, the first thing that it finds from Microsoft, this extension is required to get this behavior that you can get syntax highlighting and directly running it from this button over here. By the way, the shortcut, at least on my machine, is Control R. So you might wonder why it runs. If I'm not clicking over there, I'm using the shortcut. Okay, Python. Let's start with a simple thing. In Python, you can get a print command or use the print command to print out something to the console. Hello world would be the easiest example. And if I run this here, I get an output terminal down there saying hello world. So this is basically the first program. I invite all of you, by the way, to do the same now with me, but recording is still going on. So I think you can also take some time later on to get into this. Okay, so modify this print message a little bit. By the way, if you get any spelling errors of mine, I'm really bad in such things, so forgive me. But I'm probably not gonna do everything right here. So we said we start up in our program with an initialization phase. And for that, we assign some variables. We assign the variables M, K, D to be, sorry, give me 1 second. Because of course I have the problem ready, the program, but I'm not going to share this with you right from the beginning. But this way I'll be able to see them both. Okay, there we go. MKD, our mass will be 1.0. Our stiffness 225, and our damping parameter 1 also. So let me take the opportunity to show you a little bit about Python syntax. So how to assign variables. Python is an interpreted language. That means, as you have already seen, I can simply run it. There's no compiling step. It is just interpreted on the fly when I ask for an execution. For the downside that it is not as performant as a compiled language. Also, what you have recognized in contrast to Fortran, but as in MATLAB, if you're used to that, I am not having to declare variable types. It gets identified by the language itself. And I've also used here different ways to assign variables in that here. I just put two variables separated with a comma on the left-hand side of that equal sign and follow the same pattern with the values that I want assigned on the right-hand side. Of course, you can also stick with the classical way of each line having one variable assigned, as I did here for the D. You can also be sloppy with your declaration types, because I said the type of the variable is identified by the right-hand side of such an assignment operator. So for example, M is chosen, the type of M is chosen on the fly based on its right-hand side equivalent. This is 1 times 10 by the power of 0. And if I apply this syntax here with a power, it directly implies a float. So M, if I hover over that, at least from my Visual Studio Code here, it tells me that M will become a float. In contrast, if you look at D here, D will not become a float, because here I not implied any decimal point. This can bite you in the ass down the line, but not for this program. Just be aware that these types are identified on the fly, and that can harm you. But yeah, be aware. Okay, what else do we need? We need some parameters such as dt. dt will be our time increment. And capital T here I chose to be 200, which is the number of time steps. So from time to time I keep running so to see whether I made a mistake here in the syntax of anything. Okay. Initialize starting values. I initialize a displacement here with 0. And then I initialize my history field with 0, 0, 0. Okay, with respect to the last question, there is a displacement here, and there's the same displacement within the history field. Yes, it is there as a duplicate, but this is because this displacement here will be the degree of freedom. So just to be clear, it will be the same number in the end, always. But from the view of the program, we will have a degree of freedom field. In this case, it's a scalar. And we have a history field. And because U appears to be our degree of freedom, but also required in the history field, it is there twice. And the same will be the case in the finite element program. Doesn't harm a lot. It takes a little bit more memory, but that's just how it is. And then we need to define our external force function. So this is the first time where we need to define a function in Python. Before, we have used assignment of variables. Here, maybe novel, we have initialized h to be a vector of 3 numbers. Syntax is just so. This is a list, technically speaking. So the data type in Python for this object here would be a list, which is a little different from a vector as we will use later on, but this will work out in this case. I hope this is like readable for any of you guys. So a function definition in Python, also many ways. We will use the very simple version def. And the syntax is as follows. So def implies that we are about to define a function. F is the name of the function, and we define this function to take an argument t. The function definition will start after the double dot here. And then this editor already provides me an indentation. Python works highly on indentation. You will see the same behavior in loops. And whatever we code here on this level of indentation will belong to that function. So if I say, on the same indentation level here, I introduce the print command saying my argument is. Nice sound. And include this print command over here. Going back to the 0 level of indentation and just calling this function with say 0.0, evaluating all of this. This print command gets executed. So this comes directly from the function. So that should be enough on function definition here. Next would be we define our oscillator function. And as from what I've written down before, this oscillator function takes a material vector as an argument, a displacement, and a history field. And it returns G, DG, and the updated history field. Of course, we need to define them inside the function. G, DG, and H would be HN here. And let me just run to see whether there's an error. Of course, this is not the final result that we want from this function. Those were just dummies. And now we implement the logic. So this would be kind of what we are doing in this course a lot. We are working on the finite element subroutine to implement, in the end, our coupled equations. So at first, for this simple function here, we have to identify our parameters from the material vector that's handed in. So we might say M would be the first entry of material, K, D, and dt, sorry, like so. Okay, just for checking, I put a print command in here, which will give all these variables as a printout. Recognize that here I'm still in the function, so I'm on this higher indentation level with respect to the 0 indentation level of the main script. Also, all these variables here were defined before on the other level, but inside this function, they remain private. So K can render a different value inside this function than outside this function. Okay. Then I do the same for the history field. And I can use U here as it is. So in here, we need to compute the new history values. Under the assumption that the U, which we call the function with, is the final displacement. This will not be the case as discussed before, but will be iteratively determined in a Newton scheme. So this is the point where we actually want to implement our Newmark functions. So U, we take the same U as it is here, but we need to compute A, so the current acceleration here, as 4 by delta t squared times, and I'll be a little lazy here and copy that over. So this is the very function that we've written down before. We take the displacement under the assumption that it's the final one. We take the old displacement, velocity, and acceleration that we've obtained from the history field here. And what we get from that is the new acceleration and the new velocity. The new, once more, the new displacement is supposed to be the input of the function. Side. So now from this, we can compute the actual values for D and DG, for G and DG. And you can already imagine this is the very same structure that we will implement in our finite elements. We will first take the arguments, like read out material parameters from a material vector, which was input to the finite element subroutine. We will compute based on Newmark those time-dependent variables, and maybe then later or at first compute certain strains, certain stresses, and then implement the formulas for the right-hand side and the left-hand side, vector and metrics in terms of finite element. So this is the same structure. G would be mass times A plus damping parameter times velocity plus stiffness times current displacement. And our tangent would be mass times this parameter, damping parameter times this term plus K. Yeah, that sounds about right. Okay, you've seen me here using some syntax for multiplication, subtraction, addition. This is the exponent operator. Yeah, pretty straightforward, I guess. Okay. Then last thing we need to do is we need to We need to form a history field, which is also part of our return. And we need to make sure that this history field has the same structure as the input history field. That would also be the same in finite elements. Imagine there you don't know so much of the program as we do for this program, because we write it right now. So you must be sure, dealing with history fields, that the structure of input and output fields is the same. So what do we have here? The first would be the new computed acceleration, velocity, and displacement. So we have the same structure. Okay, let me run this. It doesn't throw an error. And just for the sake of discussion, we make a function call calling the function. And here we need to replace mat with the actual vector of material parameters that we want to hand over. The structure we have kept here in the subroutine. So M, K, D, and DT. See that we are here now on the 0 indentation level. So M, K, D, and DT will render the values on this outer level. So these values that were defined here before. And suppose we use also the history field that we have defined on top here and put a 0.0 displacement in here. Let's look at G. So we will print out G after the function call. And G will be 0. This is obvious because without any displacement, there are there is no value of 0 to expect, of G to expect. Also, we see here the print straight from this function. So M is equal to 1, K is 2.25, 225, and so on. I'll get rid of this print here. I put it as a comment. However, this is specific for you if we are working in Python on a subroutine, such as finite element subroutine, and you wonder about certain things like, okay, what's actually coming as input here? If you compute some stresses and you want to see those stresses as a value, feel free to put just plain print commands in this fashion into your subroutines, just to get an output, just to get an idea what's actually happening inside the function. Okay, let me leave this also in the script for you to check out later, but I put it as a comment. Okay, now we are starting with our time loop. See whether I missed anything. No. And for that, T is already taken. No, okay. I introduce a variable T here, which is equal to 0.0 at the beginning. So that's our initial time state. Let's start with our time loop. Okay, so our final time, number of time steps to go. Okay, that was that was just false. This is the final time. So we want to run let me put it this way. That's just easier. Okay. Okay, n steps is a variable with the number of time steps. We want to run for 200 time steps. And so we use this variable here in the loop operator. The loop, how does it work? The for loop for step in range n step is a simple loop running for step from 0 up to n step minus 1. Let me override n step here just for showing. So n step here is just 10, and inside this loop, we will print the variable step. Recognize that we end the for statement with a double dot, and that triggers this indentation level for the loop. This is then the level, everything on this indentation level will remain in the loop and will be repeated. However, the variables are not private. This behavior is just achieved for definition of functions. And as you see from my output here, the variable step, which in each loop execution run from 0 to n step minus 1. Okay, getting back to. So according to what we've written down for our flow, first thing we need to do is we need to increment the time. That will be t is equal to t plus delta t. And I put a print here to get some notification. Then I initialize my delta u, of course with 0. And then I start with my Newton scheme. And instead of, there exists, of course, a while statement in Python. Here I'll go with a for loop for the iterative Newton scheme, which I will break once the criterion is hit. Just one way to do it. So this is, of course, a nested loop. See that the editor already indents the next level. And as discussed before, first thing we will do on this level is call our oscillator function. Yeah. Okay, so of course, the material parameters will remain the same. Then we need to enter something else than 0 here. What we enter, we have discussed before. We will use our current displacement plus the displacement increment. Not dt, but du. Which will render inside the function un plus 1. Also, here we need to give a history field, which is supposed to be the history field with all known variables. For the sake of notation, we will name this field hn instead of h. And as hn is not defined here, we will define it in the time loop. With hn is equal to h. The history field h is initialized here on top. So h will be immediately in the first step get hn and entered into the function. However, if we at the end through each function call update a variable h with the new values, once we've reached an equilibrium and we allowed the algorithm to proceed to the next time step, so the loop will begin here from start, we immediately switch that back to hn. So that would be the update behavior that we described in our algorithm flow on the paper. So function call was the first thing. Then we need to add our external force, which we'll do like so. So as t, the time is incremented here in the beginning of each time step, this function will render the current value, and we subtract that according to the differential equation from the part which was delivered from the oscillator function. Now we need our criterion. Let's say equilibrium. For that we will use an if clause, if, and then we put into brackets the check. G times G is smaller than, say, 10 by the power of minus 8. And then we'll end with a double dot here. At this point, we'd like to break. So for the if, another indentation level is chosen. There's also an else if, of course, and everything that you can imagine. Feel free to Google for that. I mean, Python is one of the best documented language on the web, in my opinion. And also here, I simply use the square of our G. There is not a square root function in Python from the beginning. We will use a square root function defined in NumPy package later. But for now, this is only serving the purpose that any negative value of G is normal. By squaring, it is comparable to 0 here. Also, just for interest, we put a print here. Where we print this residual so that we can see how it becomes smaller. However, of course, this is a linear function that we try to minimize with this Newton scheme, so it should not take more than one step to reach 0. As discussed before, if this is not the case, that we break out of the loop, we need to modify our delta U using the formula that we concluded before. Yeah. And then recognize that I'm going back the indentation level of this time loop. I'm assuming that once we have left this Newton for loop, we are in an equilibrium state. So here I update also the displacement to be the displacement plus the final delta U. This update is also happening twice, as this variable exists twice for the same reason. This is supposed to be the update for the degree of freedom in this algorithm. And in the element, in terms of the history field, there's the same update happening, but with respect to the history field. Okay. Okay, I ran this. At first, nice that there's no error. There's still the print my arc is from the force function. So I'll get rid of this as well. Run it again. And here I get the time print, which I included here. So at each time step, I get a print of the current time, which is incremented by means of delta t. You can check this and it works. And I also get the print from the Newton scheme. So remember, our force function we set to 0, and now we are facing exactly the case where we argued before. What happens if no force is there? We are in equilibrium state in general, and this is reflected by the first evaluation here of the current residual. So immediately this if clause results true, and we break out of the Newton scheme. This is why we get only one residual here, which is 0. Let's say we implement the function as discussed before, and we return not 0, but 1 from this function. Now it looks a little different. And this is actually how it's supposed to look for any Newton scheme with a linear argument. So if we look at the last time step here in the print, this is time 0.2. And the first residual that we get printed here is 1450, whatever. So that's clearly not 0. And we expect the Newton scheme to propose a new delta U based on this function and try to check what happens to the residual with that. This is then the second print here, which is 4.6, but times 10 by the power of minus 24. So that's considered to be 0. And just from this, or correctly, the if clause in this case results true, and we break out of the Newton loop and skip to the next time step. Also, this happens a lot here. You can. If that was supposed to be a question, you need to be more clear. If not, I will continue. Scary. So this was happening for each time step here. And as you see, this will just work, or here it works at least. This is not a very nice output. We have just clarified from this print statements that we are able to achieve an equilibrium in this algorithm for each time step. And for this, we will utilize our first Python external module, which is matplotlib, to print out graphs of these values as they change inside this time loop. And for that, we need to import the package. As I said, there's just 2 packages that we will, or 3 packages that we will import this way. So don't get too much headache about this. We will just reuse the same commands over and over again. Imports usually take place in the beginning of a file, especially when you begin to code Python. So we say import matplotlib.pyplot as plt. So see, I'm using, of course, the suggestions from the editor, which already knows about all of these commands. This statement here just says that the functionality of matplotlib pyplot, which is plotting routine, will be available to me now inside the script by the command plt. So what I'm aiming to plot here is, let's say, the displacement over time. To do so, I need to somehow record all the displacements as they change over time. And in the end, I want to have 2 vectors, a vector where I have all the discrete time steps and a vector where I have all the discrete displacements with respect to these time steps. And then I can plot one vector over the other. So for that, I initialize 2 variables. One is times and one is disps. This here is an empty list. So it's like a vector without any entries. However, let me provide here the 0 as the first entry. So now it becomes a list with 1 entry. During this simulation now, let's say here at the end, we do post-processing. Recognize that we are on the indentation level, that this happens still in the for loop for overall time steps, but as the last thing. So we're supposed to have reached equilibrium at this point already. And here I'd like to record my current time to the times vector by using times.append t, and doing the same for the current acceleration by using disps.append u. So after for this time step, T and U are where I want them to be. I record them, I append them to these arrays. Back on the main level, let's just look at what this results. I print the variable times, which is supposed to be initially a list with one entry, but during this loop here gets appended with all the times that I will provide solutions for. And if I run that, I get this huge output in the end. So this is in fact my times vector. And see here, it ends at least with a square bracket as it's supposed to be. And by comma, I get all the subsequent values of the time that I rendered during this loop. This U looks the same, just that there the displacement is visible. And now that I have those two vectors, I want to plot one over the other, like in a graph. And for that, I use matplotlib. Matplotlib, also greatly documented on the internet with lots of examples, has different syntaxes. I will provide one syntax here now, which is supposed to be sufficient for this course, I guess. So you can reuse that for any case where you want to plot one vector over the other. However, there's, in the end, also in view of the project at the end of this course, I'm fine with any syntax that results in plots, at least if everything is correct. Okay, so fig.x. By 2, let me say 1 by 2 of fig size is equal to 10 by 5. Okay, so in fashion of any cooking show, I have prepared something. And I will briefly tell you what all of these lines mean in a second. So this times we want to plot times over displacements, position, and let's see how it goes. Plot 1.2. Okay. Too many indices, sure, here I have only one. And here we go, okay. I think you don't see the plot right now. Kathy, can you give me a thumbs up or down?
No, Sasha, the plot is not visible.
Okay, then I need to close the reference solution and share my whole screen again. Okay, here we go. So, what did I get from this? Okay, so as you see, this is a plot with two subplots, and this is steered by this command here. Plot subplots just is responsible for the layout of this window. The first entry is the number of rows for the subplots, and the second entry, the number of columns. So one row, but two columns here. I think for the second plot, subplot, we can fill in the velocity in a minute. And as I said, this will be repeated a lot, so don't panic if you don't understand it by now. We will, with these blocks here, we will fill individually each of those subplot. Axis here is the variable where the subplots are assigned to by this command, and figure is the overall figure. The index here is responsible for the subplot we are addressing with the following commands. 0 is, of course, the very first subplot here. The first command here means that to this very first subplot, we'd like to plot the vector displacements over the vector times. Color is specified to be black. Of course, you can also put in here the descriptive blue. Line width is the line width. Many more options exist. Feel free to Google for it. Further, as we are doing appropriate plotting here, we'd like to set a title to this first subplot, which is position. That's rendered here. And we also like to name the X and Y axis using the methods setXlabel or the commands setXlabel and setYlabel, where we specify here the text, time, and position. See time and position. Also here you can use different colors, etc. pp. Recognize that although we say position here, we are plotting the displacement, but we have concluded before for this specific example, this is identical, so that's okay. On the x-axis here, we can see all the time steps, and here the concerning displacements as they are recorded in these vectors. At least for the time steps, we can clearly say the last time here in the output is 0.2. So we can see this is really like the last point also that is rendered here in this plot. And at first, let's do the same for the velocity. So I prepare the concerning subplot for that. The next plot will get the index 1 here from this axis variable. I can reuse the times list for that plot. And here I will use a new vector vels for velocities. The color this time is green, just to make to have some fun. Everything else is the same, of course, with different label and Y label. To record the disks, I start up with a almost 0 vector, and within the simulation, I'd like to append the velocities. How do I get the velocities here? Well, we have said that the velocities are saved in the history field, and if we've reached this point of the simulation, we have exited the Newton scheme. So the last time h was overwritten, this is supposed to be the valid history field. And we have defined before that the velocity is the one entry, so the second entry technically, but in Python language, the one entry of this list. So we can access this the h field like so. Pretty straightforward, isn't it? So I know all of this is much if you haven't seen Python before, but for your motivation, compare it to dealing with or achieving such a plot with Pheeb. And I can assure you with the Python, with the FEM code that we will use, it is like the same. I will not say easy as this, because I know right now this might be looking complicated, but you get used to that very fast. I've seen that in the last semester where we had this course, and you will learn to appreciate it. Okay, I click run again. And now I get this output. So the velocity also starts with 0 here, and it will describe a curve very similar. Similar, I mean similar to the position, which also starts with 0. And yeah, this curve, which looks similar to that curve, is actually an oscillation, a sinusoidal oscillation. I guess the sinus function starts at 0, or is it a cosinus? I always forget about this, but you know what I mean. It's exactly what one would expect for the motion of such a single mass oscillator, which is an oscillation, a harmonic oscillation actually, if no interruption for the external force is given. We can investigate this by spending a little more time steps. Let's say 2000 time steps. Of course, the simulation takes a little longer to run, and I get spoiled with a lot of output. And as you see here, the result now in the plot renders from time 0 to time 2, not 0.2 as before. And we can investigate this oscillation further. We can see that this is actually a damped oscillation. So the amplitude of the oscillation will decrease, although the frequency of the oscillation will remain constant. This damping behavior here is absolutely expected because we've put a damping parameter here in our material parameter scheme. Let me get rid of this damping parameter, and what we would expect is the same oscillation behavior, but without any decrease in amplitude. And if we run this again, we get proof of this. Another point, when we compare position and velocity, you have seen this example before in some other mechanics course, I guess. So you know that there's even theory to compute this oscillation frequency and amplitude from these material parameters of this problem. And you might know that the velocity exactly is oscillating in the same fashion as the position, but just with a shift in frequency. It's not a different frequency, but it's a shift. So by comparing these, we see exactly this shift, and this is just a good indication, or just take this as an indicator for that the Newmark scheme that we use to express the velocities in terms of the displacements, that this is working in it's a valid assumption, because at least for this example here, it renders the expected behavior. Okay, there's one more thing that I'd like to do here before I leave this little script to you, which is implementing the other force function. So right now we have the force of 1 applied to the system constantly over the whole time. This is what leads to this oscillation behavior, or to this harmonic oscillation behavior. Let's say we implement our other function. And in order to do so, remember this was this function where we increase linearly with time and then abruptly jump to 0. We use if clauses for that. We say if our argument time is smaller than, and let's say the simulation now runs for 2 seconds, say 0.3 seconds. Up to 0.3 seconds, we increase the load. So if this is the case, we return t, the time itself, to be the load. Else, and there we go with if and else, we return 0. So this is, if spelled correctly, this is an example for if else, and also where a function returns different values at a certain argument. Okay, let's run the simulation with this different not as expected. Let's say 3 times t, so just increase the load a little bit. Let me decrease mass and damping here a little bit and run it again. Okay, that looks at least a little bit better. All right, so result looks different. First thing I'd like you to recognize is if we look at our output here, we still see that the residual for each time step is a certain number in the first place and then 0 in the second place. So even with a change in the force function, our algorithm still yields equilibrium. Guys, this is critical. Remember what you've done in FEEP before, where you also looked at a certain number and you actually were aiming for a 0 approximation in that number to have a correct result. The very same is true here in dynamic analysis for each individual time step. I mean, if we start programming a finite element, you will also look at these numbers again, and you are also looking for a 0 here. If you don't get a 0 or an approximation of 0, then you have a problem. Your code is not working correctly. Actually, for a linear problem, and I will tell you once we reach the first nonlinearity, you expect the second call of the residual to be 0. I hope all of you remember why this is the case. And I'm just saying, if you start working on some code on your own, always have an eye on the residuals. Don't expect them to be just like so anytime. Okay, let's take a look at the result. And the result looks different in that at a certain point here, we have an abrupt change in the velocities. Same is visible here in the position, and the time when this hard change happens is exactly 0.3. So this is where the load changes. The load is linearly increasing up to that point. Recognize that at the increasing of load, also the position gets, or the displacement grows, even though there's a little dynamic effect, there's a little wave that we can investigate. We are also growing our displacement until as the load grows. So just what we expect. And after the load is released from the system, after it renders 0, the displacement goes down. But because of a certain mass, we've built up, imagine if the mass swings back, we build up some inertia. And due to the effect of inertia, the spring will go more in a negative regime here with respect to the displacements as we've started with, just because of inertia. And then we are actually at a position where the external force is not there anymore, but still the system shows some displacement and velocities. This is just the effect of mass inertia. Yeah, imagine you have a physical equivalent of this single mass oscillator, and you by yourself extend the mass, or you extend the position of the mass so that the spring is under tension. This is kind of also not happening abrupt, so in a nanosecond or so, but just linearly in time. And then you release the system. This is like there were no force externally applied. And then you can also imagine that the spring will go a little bit like this for some time until any energy is dissipated out of the system. And this is again what we see here as a damping in this post-force behavior. Okay, so I will, of course, share this very first script with you guys. I will upload that in Moodle. And if you have not done it simultaneously with me, try to replicate the steps that lead to this code, because as I mentioned so often, this is like the same algorithm that we have in finite elements. And especially with time-dependent variables, it's a very good thing if you understand this properly. It will help you to achieve a good mark in this course. Also, what you should take from this are some basic Python steps. Like I said, there's just, say, 3 or 5 more commands that you need to learn in Python, like specific to this language, to achieve everything in this course that you wish for. So please go over this file, try to replicate it yourself, play with it, because with dynamic effects, it's really good if you have an understanding, if you can make arguments, just as I did for the results that we were seeing, for the behavior of them. Maybe if you want, I can imagine try to make a third plot here and plot the acceleration. That would be a good training task for you. Try to plot the acceleration as it changes during the simulation. Try maybe another force function, something that comes to your mind. An idea would be linearly increase the value of the load and then just keep it constant at this level. Don't release the force, but keep it constant. And last but not least, try different values for the material parameters. So for example, if you increase the damping, of course, you should drive the system into a steady state solution where no oscillation happens anymore.